All right, welcome back. We're just going to revisit Green's theorem. You may have remembered Green's theorem stated this. Now let's do it in a different color. Green's theorem, the basic notion of it was that if you had a line integral or a loop integral of p dx plus q dr, that was the area integral, right, of the partial with respect to x of q minus the partial of p with respect to y, and that was an area integral. Now, we can restate these in terms of the vector fields, in terms of the curl and the gradient. So, let's say that we have our vector field. Let's say it's just x and y. So our vector field is p of xy, q of xy. Okay. So here we have, on the left-hand side, we have the integral over the loop of f, that was dy here, I got ahead of myself, dotted with dr, okay, equals, on the other side, what we have is we actually have the k component, or I'm sorry, the 3 component. What am I doing? Getting everything mixed up. But it's the third component, or the z component, of the curl. Okay. And actually, the curl of f by itself, if you calculate it, since the z component is 0, since the z component is 0, these are all zeros. Okay, and then the z component is exactly that. Partial with respect to x of q minus partial with respect to y of p. Okay, you can think about it like ijk, partial with respect to x, partial with respect to y, partial with respect to z, p, q, and 0. Okay. So, the I component, you're going to take partial with respect to y of 0 minus, there's no z, right? These don't have z, so that's also 0. The j component, partial with respect to z, that's 0, minus partial with respect to x of z. So the only thing is the k component, which is going to be partial with respect to x of q, minus partial with respect to y of p. Okay, so that's just another way to see Green's theorem.